Hello to everyone. Welcome to this session, which is related with solid state materials and open devices and integrated circuits. We are going to start with a presentation by Luis Elias Salgado Solano, whose work is titled Convolutional Neural Network for Multi-Channel Conversional Analysis Applied to Reading Fault Detection. Thank you very much for your attendance. I'm going to show you my presentation. We belong to this center. We are from Ciudad Mexico City. This work is titled Convolutional Neural Network for Multi-Channel Vibrational Analysis Applied to Very Fault Detection. Well, let's start. These are the contents we are going to address in this presentation. Well, first introduction. Some important points are going to be addressed in this work. The main goal of this work is to classify and distinguish between failures in using vibrational data to classify vibrational analysis. We propose a convolutional neural network to solve this problem with large datasets. And this approach was developed to analyze experimental signals from two accelerometers. It's a multi-channel analysis in this work. And well, let's start and go. First, the motivation. The motivation is because presently vibrational analysis has grown in industry, in science, and technology, and we are proposing a different approach. Frequently, in which has been proposed the use of machine learning, convolutional neural networks, wavelet transform, among others. However, our approach is different. Well, we are going to talk about how the database is organized. This database is organized by vibrational analysis sampled by 2,000 samples per second. These datasets are available from the Case Western Reserve University website. And these datasets contain vibrational data from two different sources. And this data has been categorized by severity using three different diameters. And well, generally speaking, is how the database is organized. Data adaptation. To use convolutional neural network with this kind of data, we need to make some adaptation to the data. And this adaptation comprises 3 stages. And the first one is to split the general vector into 256 element samples. These samples are later reshaped in a matrix. As you can see, in the first stage, we have vectors. In the second stage, we have matrix. And finally, these matrices are joined to create a tensor. Bidimensional tensor, which will be analyzed in a convolutional neural network. And well, what a convolutional neural network is. Generally, this model is a neural model which has been designed especially for classification and regression. And these models have some interesting features. In the how can be seen this approach? As you can see in the equation 1, we have this expression. This expression can be translated graphically. As you can see in the first one, in the first stage, we have a matrix. Later, we have kernel, and finally, we have an output. The output is the result when we operate enter matrix and kernel. And this is the result. A general, and more generally, for stacked layers, the expression is as seen in the equation 2. And these are the examples. Methodology. How this methodology is composed? This methodology, in the first stage, we have the 256 element vectors rearranged and adapt into tensors. Later, we have a feature extraction stage by convolutional layers. And finally, we have a classification stage using dense layers. How this network has been built? Well, there are the parameters in this table shown. As you can see, we have 6 convolutional layers, 3 dimensional reduction layers. The convolutional layers are named COM2D, and the dimensional reduction is max full, and finally the linear are dense layers. This is the architecture and training. Finally, the training. This network was trained using stochastic gradient descent as optimization algorithm. The loss function was chosen as cross entropy. The learning rate was set to 1 times 10 to the minus 3. Momentum 0.9 and batch size 500. After the training, a criteria to evaluate the performance of the model commonly used is these 2 graphics, which is the loss graphics. As you can see, we have some different behaviors. In the left side, we have a more stable behavior in optimization during minimization. And in the right side, we have less stable behavior. It depends, this behavior depends directly from the optimization algorithm parameters, from the network, and the nature of datasets. And in this case, that difference can be explained because in the left side, the graphic is by the use of just one case of severity. In the second one, we include all cases of severity. This is the main difference between them. And as you can see, there is some features, some remarkable features. Finally, experimental results. These experimental results have been tested, and we believe that has been successful. In the first table, we have the outcomes for one case of severity and diameters. As you can see, we achieved more than 99% of accuracy for both cases, training and accuracy and test. Well, this has been successful. However, in the other cases of severity, we have poor performance, but not at all. As you can see, we accomplished above 90% of accuracy in both cases. And finally, we join all the cases of severity and loss to make a general database. And the final result is 99.3% for training and 99.1% for test. A way to see this graphically is using confusion matrix. As you can see in this below, we have two confusion matrices. One belongs to training and the other one to test. An ideal confusion matrix have all the elements in the main diagonal. As you can see, these are not ideal confusion matrix. However, its shape is similar and its performance is good for us. Classification has been successful, and these are the results we are reporting. And contributions. Recent technical works have addressed vibrational analysis using convolutional neural networks, which involves preprocessing stages such as frequency, division, and denoising, image classification that contains time and frequency domain information, single channel analysis, among others. In contrast, our multi-channel method avoids this kind of signal processing, whose outcome is competitive with others. It's the first time we report this kind of analysis. This analysis has never been reported previously, and this is our contribution. And limitation. Despite these outcomes are successful, we cannot compare our work with another report in the literature because we didn't include a noise analysis to make a fair comparison between them. That's why we are not comparing this work with others. And the second one, as you know, convolutional neural networks are deep learning models and needs lots of computational resources to make trainings. That's why we need at least engineers and graphical engineers to execute the training in these models to obtain reasonable period of time for training. And finally, this architecture cannot be included in small computers like Raspberry because it needs additional optimization in the architecture. Conclusion. The methodology presented in this work shows good results for the vibrational data analysis on the different loads and paper severity conditions showing a high degree of flexibility and accuracy. This work lacks noise analysis to make a fair comparison with similar works. And the architecture used in this work is an optimized model that is lighter than pretended models such as ALESNet or ResNet. It's worth to emphasize that this architecture was designed by us. We are not taking models from internet or from another sites. We create the model and we test the model. And there are some references used in this work. And that's my presentation. Thank you very much for your attention.
Thanks very much for your attention. Now we have maybe 1 or 2 minutes for questions or comments. So start.
For your optimizer, why did you use that kind of optimizer? Does it grading. Why did we do that? Why did you choose another?
It's a good question. We experimentally proved some optimization algorithms, like Alan, for instance. However, the convergence wasn't the same. And the experimentally observed the behavior and corresponding to stochastic dynamics.
Why do you say that it shows a best behavior then?
So we made a lot of
Okay,
that's
for it was with the results, it was the time, computing,
but that's interesting. Can you put the slides?
One?
The presentation.
okay.
Please put it left. Right. We've seen some this behavior in some cases. And we set a goal, for instance, 0.01 to achieve. During the training, stochastic gradient descent shows how can I say convergence very well. Its convergence is faster than in other algorithms and take less effort to achieve the goal than other methods.
Thank you. Still another question or comment?
Yes,
Okay.
I have a question. I don't understand why are you comparing both the graphic in this slide? Because the first graphic is you are analyzing just one kind of duration, right?
Yes.
And the second one is all the duration. What
Yes.
is the goal to compare both graphics in this case?
That's a good observation. Because we have more variables in this case than in the other. And that's why the convergence is less steep. It's a way to visualize how the optimizer converges to the optimal solution. And as you can see, in the second one, it takes more effort to achieve the goal than in the first one, because there is more information in the system, more data include more cases, and we can see that the data is richer than the first one. Thank you so much.
Okay, we stop here this presentation. We appreciate your participation.
Thank you.
Thanks very much. Continue session with the same presenter. Now is going to present a work called approximating eigenpairs with general levels by loss function minimization.
Thank you very much again for your attendance. I'm going to show you my next presentation, which is the title Approximating Eigenpairs with Neural Networks by Loss Function Minimization. Right, let's start. These are the contents we are going to talk about and go deeper in the next slides. Introduction. Well, In this work, we approximate all the eigenvectors and eigenvalues of asymmetric matrices by minimizing an appropriate loss function along with linear single neural network. The numerical accuracy of this computational method was evaluated, confirming its effectiveness for the cases of medium and large dimension matrices using the Adam optimizer and its variant AMS graph. With applications, there is lots of application of eigenvalues and eigenvectors, especially to observe physical phenomena. And a practical case of this is in cyclotrons. They use eigenvectors as well as in lots of cases. This problem has been addressed in computational paradigms like quantum computing. And let's start. I am going to talk about methodology we use in the development of this work. Well, the methodology. The computation of eigenvectors was proposed as a minimization problem. We use a linear single-layer neural network with its synaptic weights are expected to be the eigenvectors matrix. This minimization problem was performed using two stages. In the first stage, we first approximate the eigenmatrix completely. In the second stage, we handle each eigenvector individually and minimizing loss function we propose in the work. And finally, we are going to talk about the results. And this methodology was described in Python languages using Python's deep learning tools. We are going to talk about the model we use in this problem and in this work. The model we use is shown in the image at the right side. As you can see, it's a single-layer neural network, which includes a synaptic weight matrix. As you can see, is W. An input matrix is A, and output matrix is B. This is the architecture we use, and this model can be mathematically described by equation 1, where it states that A times W is equals to B. 8 times W is equal to B. This work was developed to symmetric matrices. A way to create the easiest way to create a symmetric matrix is using the equation 2. This matrix was created using random uniform values from -1 to 1, and the way to perform or to achieve this symmetric matrix is using equation 2 that says that A is equal to the transpose of Q plus Q over 2. The loss function proposal to achieve the goal and the desired behavior, we have to consider the eigenvalues and eigenvectors properties. And in equation 3, we have some properties. It states that A times Z corresponds to the eigenvector matrix, is equals to the eigenvalues multiplied by the same eigenvector matrix. This property was taken and was adapted to use the neural networks. There is an equivalence between this property and the neural networks. As you can see in equation 4, we have the term in the left side of the equation 3 are the analogy is for neural networks is equals to A, the same matrix multiplied by W, which is expected to be the eigenmatrix, the eigenvector matrix. And this is equals to B, the output matrix of the architecture we propose. Well, the analogy also includes question 5, which says that the eigenvalues multiplied by the eigenvector matrix is equals to the diagonal of the matrix of the result matrix of this product, as you can see. And well, we are going to explain how our proposal, our loss function proposal was built. Well, there is some consideration in order to avoid most of the local minima problems. And well, we have some interesting expressions in this equation. And the first one, at the denominator and the quotient, we have a term which is included to avoid trivial solution, because sometimes minimization leads to the zero solution. Well, the second one in the numerator of the quotient, we have an exponential factor. This factor is included to lead minimization towards an orthogonal solution. And finally, in the other factor, this includes the properties we talked about, as I mentioned before. And well, these are our proposal. This is our proposal for minimization. Another consideration to avoid problems, especially during optimization and training, was to set an initial matrix distribution. It was experimentally observed that the behavior and the convergency has a correlation between the dimension of the matrix, initial matrix, and the first loss value. As you can see, we have an exponential behavior that increases when the dimension increases with an exponential correlation. Well, a way to avoid this is initializing the initial matrix of weights using an orthogonal weight matrix. This orthogonal weight matrix was proposed to be a hardcore listing space, and it removes this problem. How the algorithm was performed? As I mentioned before, this algorithm was performed in 2 stages. The first stage was performed using Adam optimizer algorithm, which compute the full eigenvector matrix. In the second stage, we use AM's graph, that is a variant of Adam algorithm. And we're going to talk about the approximation stage. This first stage was performed using Adam as optimization algorithm. The loss function was set to be equation 7. The learning rate 1 times 10 to the minus 4. The bias is bias mode. And the goal is to achieve loss value below 1 times 10 to the minus 12. Fine tuning? Well, once the eigenvector matrix has been approximated, we need to handle the eigenvectors individually, minimizing the same loss function. However, we need to change the optimization algorithm because of convergence problems. It was shown experimentally that AM's graph has better behavior in convergence to solve this problem, and because it has been tested for non-convex problems and have good performance with these gradients. This is the algorithm, pseudo algorithm we use to handle each one of the vectors and ensure the convergence and the likeness of each one of the eigenvectors. And then we have some graphical resources to explain that. In the left side, sorry, we have computational. This is obtained by common traditional algorithms, and the second one is obtained by our proposal. As you can see, the likeness is good for both cases, the full matrix. However, the order is different. Another criterion to measure this performance is to compare digit by digit each one of the values. And here we have the distribution of similarity for a 50 by 50 matrix. As you can see, most of the values have at least nine digits of precision for the eigenvectors, and for eigenvalues, at least 12 digits of precision. Contribution. There's some interesting contribution in this work. This is the first time that the eigenvectors matrix has been computed successfully using neural networks. And the second contribution is that we propose this loss function, and these are our contributions. Conclusions. Despite we obtained some good results, some limitations remain in this work. These limitations are the lack of convergence in conditional matrices. As you can see, in a lot of the cases, we use an ideal matrices. However, in conditionals, we couldn't achieve convergence. The other limitation is that there is no solution for matrices whose dimensions are larger than 50 by 50. There are limitations observed in this work. And finally, references. We use some references, and that's it. Thank you very much for your attention.
Again, with the voyage process of comments. No. He still here for the presentation. What we should do next. That's the first special.
¿Y ahorita o qué está pasando?
We may continue this session. I am asking for Pablo Varela, Roberto Moff.
Son live.
Sorry. You may start your presentation. Let me introduce you. The work people from Illinois is presenting right now. It's called derivation of a fixed expression for an RTWO oscillator based on its geometry and topology in CMOS technology. Okay.
Hello, are you listening me?
Yes.
Okay.
Yes.
Thank you for the presentation. Yes, I am Juan Pablo Sanavarela, and together with my advisor, Dr. Mónica Linares Aranda and Dr. Robert Star Murphy Artaga, I will present our work. This is the outline of the presentation. First, I will introduce the background of these oscillator, and the objectives of this work. Then I will focus in the geometric analysis of RTWO, considering polygonal structures, bevel corners, and the effect of the Möbius crossover. Next, I will present the proposed mathematical model and the simulation results. Finally, I will conclude with the main finding of this research. Okay. RTWO, or rotatory traveling wave oscillator, are an attractive alternative for generating high frequency signals. Okay. They offer several key advantages as a noise tolerance, low power consumption, and easy CMOS integration. However, one of the main changes is that design is high sensitive to the small geometric variations, especially in high frequencies. This motivates our work to develop a geometric model that directly links oscillation frequency with physical dimensions and the topology. In the figure, we can see an example of this structure when typical Möbius crossover and corners. In this other figure, we can see the relationship between oscillation frequency, total length, and integration area. And we can determine that the smaller structure use less area and achieve high frequencies. Okay, the objective of this work are a fourfold. First, to perform a geometric analysis of RTW structure. Second, the equation that parameterize the design as a function of physical dimensions, conductor width, spacing between rings, and total length. Three, to develop a mathematical models that relate oscillation frequency to geometry and the topology. And finally, validate the proposed model through simulations results. This is other example of RTWO. Okay, this oscillator can be divided into NC equivalent sections depending of the topology. So we defined two important parameters: the parameter LL, which represent a direct geometric measure of the other contours, literally distance between this corner to this corner, and the parameter LT, which is adjusted length and depends on the parameters L, W, and S. In the figure, B represents a simplified version of the structure, where the total path length can be approximated as the sum of the inner and the outer contour. This approximation is the base of the geometric analysis. From the geometric approach, we derive the expression that relates the adjusted length LT with the number of sessions NC and the dimensions L, W, and S. The question shown here allows us to determine the proper scaling for RTWO with polygonal resonators. For example, if NC is 4, corresponding a square topology, this expression simplified to this, which provides a direct way to estimate the total path length. In the figure, we can see the corresponding angles of the geometric analysis and the parameters LL and LT. Okay. When analyzing the square RTW topology with 45 bevel corners, we found several key advantages. The bevel geometry reduced the reflection and the corners, improving the energy circulation and overall performance. It also maintains a easy integration within CMOS process. The analytical derivation shown here results in expressions that relate the parameter LL with the dimension L, W, and S. This equation quantifies how the b-ball geometry reduces the effective electrical length of the resonator. In the figure, we can see the b-ball corners and the structure in general. Okay, here in this part, we analyze the effect of the Möbius crossover. This structure singly increases the total electrical length and therefore modifies the oscillation frequency. The geometry introduced an inclined crossover section divided by the angle theta m, which is typical 45 degrees in CMOS technologies. The expression shown here relates the modifier like L3 to the physical dimensions W and S, as well the crossover angle. These analytical terms helps quantify how the crossover contributes to the phase balance and the frequency derivation in practical RTWO layouts. Here it's important to say the parameter LT is the distance between this border to this border. Consider the inclined section. Okay, here we summarize the geometric results obtained. This equation allows us to calculate the specific length of the resonator considering his physical dimensions and his topology. On the left, we have a general expression for polygonal structure, which depends on the number of size. On the right, the case with 45 b-ball corners. This expression provides a foundation to integrate geometry into the mathematical model of oscillation frequency. It's important to say that this equation considers that theta m is equal to 45 degrees. Traditionally, the oscillation frequency of RTWO is estimated using the simple LC relation shown in the question number 1. While this expression is easy to apply, but it neglects the geometric and topology characteristics of the structure, leading to an error of to a 30%. To improve accuracy, we derive an alternative model showing the question number 2, which expresses the frequency as a power law depends on the physical dimensions. This formulation significantly reduces the estimation error and better represents how geometry affects the oscillation behavior. The diagram of the right summarizes this comparison. The conventional model is simple in accuracy, whereas the proposed model is most precious through it requires a multi-time geometric analysis. In this slide, we refined that the model by expression is a modified power laws that include 3 new parameters, A, B, and C. The parameters A and B depend directly on the physical dimensions. By defining A and B, we can generalize the model to predict the oscillation frequency for any RTWO geometry. The table on the right summarizes 3 experimental series show how both parameters vary with the structure's dimension, supporting the dependence assumed in the question number 3. Here, we have troubles with these results because the results in the table show that the relationship between parameters A and B is not very sensitive to the dimensions W and S, but it's also possible to generalize a relationship. We are working in this part. Okay, in this slide summarize the validation of the proposed model. The question number 1, black line, which only consists the total leg, produce a large variations, up to 45% error for a small geometry. In contrast, the question number 3, which incorporate geometry and topology parameters, achieve error below 1%. To the plot clearly show how the new approximation follow the simulation result for all configurations, demonstrating that the proposed model greatly improves prediction accuracy. Okay, finally. The equation derivatives in this work provide a practical design tool for sizing RTWO with high accuracy. The proposed model not only reduce reduce the frequency estimation error below 1%, but also introduce a framework that relates geometry, topology, and oscillation behavior. It's necessary to establish a relationship between the coefficient of the modifier power length model and the oscillator physical dimensions. The proper selection of the geometric parameters contribute to the optimization of integration area. And finally, the proposed geometric analysis, together with the frequency approximation method, allows for a consistent cooperation between different configurations under equivalent conditions. And that's all. Thank you for your attention.
Okay, we stop here with this presentation, but there is still time for questions for Juan Pablo, who is online.
I have a question. Could you please explain briefly what aspect of topological aspects, such as the type of connection, symmetry, or the use of a Mobius connection, have the bigger impact on frequency in how it is reflected into the equation?
It's minimal, the increase of this structure of the Mobius structure, but for example, when I try to achieve high frequencies, this linear increase of LED produce large variations. For that reason, we decide to analyze this structure.
Okay. Thank you so much.
Any other question or comment around? No, we appreciate very much to Juan Pablo your participation. So thanks very much.
Thank you.
Está ahí. Del medio.
So who's going to present the next? Es Julio Alamillo. Oh, sí, you're good. Okay. We can start a little bit earlier. So Julio Alamilla Rios is going to present the work title Evaluating the Behavior and Robustness of State-of-the-Art Physically Unclonable Functions UFs against machinery attacks. So go ahead, please, Julio.
Did you hear me? Do you hear me?
Yes, we can.
Okay. Good morning. My name is Julio Lamilla Rios, and the title of my article is Evaluating the Behavior and Robustness of State-of-the-Art Physically Unclonable Function proofs against machine learning attacks. This presentation consists of 5 topics: an introduction, background, selected and analyzed architectures, results, and conclusions. IoT devices represent a major technological revolution as they can connect everyday objects to the network, enabling real-time data collection, storage, and processing. Although these devices are highly efficient, they face several challenges when being integrated or implemented. Among them, security is the most critical one, owing to the large sensitive data they process. One of the most effective solutions to enhance security is the use of physically unclonable functions, or PUFs. These mechanisms rely on the inherent physical variations that occur during the semiconductor manufacturing process. The main advantages of these mechanisms include uniqueness, robustness against attacks, minimal resources for its implementation, high scalability, low power consumption, compatibility with other existing technologies, and a high level of security. These mechanisms are divided into two categories, weak proofs and strong proofs. Weak proofs generate a small challenge response pair space or CRP space and are typically used in devices with low or medium security requirements. In contrast, strong proofs produce a much larger CRP space, making them suitable for authentication and verification applications in IoT devices. This work focused on strong proofs. To evaluate the quality of a proof, certain parameters known as proof metrics were used. In authentication, the most important ones are security, which measures how robust the device is against attacks, uniformity, which determines the randomness of the responses, and uniqueness, which indicates whether each device is truly different from other instances of the same architecture. To avoid starting from scratch, this research conducted a qualitative analysis of 13 architectures, from which 4 were selected based on their implementation year, complexity, and how closely their metrics and robustness against machine learning attacks approach ideal behavior. The architectures highlighted in green represent arbiter-based proofs, while those highlighted in red are based on SRAM architectures. Once the architectures were classified according to the type of proof cell from which they are derived, it was important to analyze each one in depth to understand their operation. The first architecture is the reconfigurable memory proof or REMC proof. As shown in the figure, this design exploits the natural entropy of SRAM power-up states to generate unique CRPs. Its core consists of 5 SRAM blocks connected to a multi-level control logic. Each 64-bit challenge is processed through address-based SRAM readings, cascade XOR operations that introduce nonlinearity and dynamic reconfiguration controlled by 8-bit inputs, enabling multiple responses for the same challenge. The next architecture is a reconfigurable SRAM, which transforms conventional SRAM cells into a strong proof capable of generating multiple CRPs from a single cell. Its operation is based on dynamically modifying the metastability point of each cell through additional transistors in the pull-down and pull-up networks controlled by a multi-bit challenge. This mechanism allows each challenge to alter the strength balance between the cross-coupled inverters, producing unique responses dependent on process variations. Furthermore, the design includes a response instability detector to discard unreliable bits and a scramble based on a Galois linear feedback shift register or LFSR, which introduces additional randomness. The next proof analyzed was the response feedback based lightweight anti-ML attacks proof, which combines an arbiter proof with a reconfigurable Galois LFSR in a closed loop system, aiming to enhance security against modeling attacks. Its operation consists of three main phases. The first is challenge obfuscation, where the LFSR dynamically transforms the original challenge into a variable sequence of new challenge for the proof. The second phase involves response feedback, where each output bit of the arbiter proof or A proof randomly modifies the feedback polynomial coefficients of the LFSR. The third phase introduces secondary confusion, in which the accumulated responses reconfigure the LFSR again to generate the final output. This bidirectional interaction between the LFSR and the arbiter proof ensures that each response influences subsequent challenges. Finally, the fourth architecture analyzed was the randomized proof. Its operation is based on dynamically randomizing the input challenges through an integrated random number generator, or RNG. The architecture consists of three main blocks, a challenge randomization module controlled by the RNG, and LFSR register that expands the response into multiple bits, and arbiter proof responsible of generating the final response. With these four architectures, a quantitative analysis was performed based on simulations that allowed the evaluation of key proof metrics. This analysis was carried out using the Cadence digital design environment, while the data processing and evaluation were performed in Python through the Google Colab platform. Using these simulation tools, a fully reproducible experimental flow was developed to this environment. The four proof architectures were described in Verilog, and using a test bench that controlled both the generation of challenge and delay variations. A total of 10,000 random 64-bit challenges were applied, generated with the random command and a fixed seed to ensure reproducibility. Additionally, random delays ranging from 10 to 40 nanoseconds were introduced to emulate physical process variations. The responses were then analyzed using Python libraries, where the main proof performance metrics was evaluated. Finally, with the scikit-learn library, the robustness of the architectures was evaluated against machine learning attacks, considering three attack types: support vector machines, or SVM, neural networks, and logistic regression. Once the methodology was defined and the simulations were completed, the analysis of the obtained results was carried out. In this section, I present the main metrics and the observed behavior of each evaluated architecture. The first metric analyzed was uniqueness, obtained through the intercoming distance. This metric depends on the Hamming distance between two instances of the same architecture, the number of bits in CRP word, and the number of instances analyzed. In this case, was 4. The ideal value of uniqueness is 50%. If the value is higher, repetitive patterns may appear, making modeling attacks easier. If it is lower, several instances may produce similar responses, reducing individually. In this graph, it can be observed that the proofs and that the PUFs with uniqueness values close to the ideal are the reconfigurable SRAM PUF and the FLAM PUF. The second metric analyzed was uniformity, which depends on the Hamming weight of the PUF responses. That is the number of bits that are 1 in each output. This metric was calculated from 10,000 responses, and similar to uniqueness, the ideal value is 50%. If the value is higher, most of the responses tend to be logical ones. If it is lower, zeros predominate. In this graph, it can be observed that the reconfigurable SRAM PUF and the REMC PUF show value very close to the ideal, indicating a good balance between zeros and ones, and therefore a high degree of randomness in their responses. The next step was to evaluate the resistance of each architecture against modeling attacks based on machine learning. These graphs show the prediction accuracies obtained by the three attack types as a function of the number of CRPs used for training. The ideal prediction accuracy is 50%. 50%, as it represents the point where the model cannot predict the responses better than random guessing. If the accuracy is above this value, it indicates that the PUF is easily modelable. The results show that the PUF with simple obfuscation techniques or few randomization stages are more vulnerable to modeling as RPUF and REMC PUF. In contrast, designs with stronger obfuscation, such as the FLAM PUF and the RSRAM PUF, exhibit higher resistance, reducing the predictive capability of machine learning algorithms. In summary, considering both the performance metrics and the resistance to modeling attacks, the results show that the FLAM PUF and the reconfigurable SRAM PUF offer the best balance between uniformity, uniqueness, and security. Both maintain values close to the ideal 50% and exhibit low prediction accuracy on their machine learning attacks, indicating high modeling resistance and therefore more reliable behavior for secure IoT device applications. Finally, achieving high uniqueness and strong resistance to machine learning attacks remains one of the main challenges in hardware security for the Internet of Things. Even though some architectures exhibit good statistical metrics, machine learning models can still predict their responses if proper countermeasures are not applied. Also, this demonstrates that randomness alone is not sufficient. Robust design and obfuscation techniques are required to strengthen authentication mechanisms. And finally, modern PUF architectures must integrate physical randomness, modeling, resistance, and energy efficiency to ensure secure and practical implementation in IoT environments. Thanks for your attention.
We are going to ask a question or comments around questions or comments.
I have a question. The who is it a circuit, but in this work that was presented, it's the theory so we can evaluate which one is better, right?
I don't get your question. Sorry, can you repeat it, please?
Yes. My question is if the book is actually a circuit, but in this case you simulated, which one it can be more accurate?
Do you ask me if the PUF is the only circuit that has a high level of security, or if there are another circuits that are capable of obtain this high level to in IoT applications? Sorry,
Well, it wasn't that my question, but I think that clarified the one that I had. But still, if you want to answer that, it can be interesting.
sorry, I don't get your question. If you can you write them in the chat and I question, please?
Acerca. Still, 2 seconds,
Where's the
please.
mic?
Thank you so much. Just I wanted to know if the PUF is it a circuit and that you are just modeling how it works, and then based on this we can say like which one it is the one that can give us more uh, that it can make a more secure system, right?
Mm-hmm. PUF is
Okay.
Mhm. Sorry.
And also, I would like to know that question that you were thinking I was making, that you say if it exists another type of circuits, it can be interesting to know.
If exists another circuit that seems the PUF behavior for IoT applications, yes, but the PUF is the most reliable because generates CRP random random responses to a fixed challenge.
And I have another question, because I didn't understand it. For example, I saw the numbers that you presented, and it says 50%. So it means they are not super secure, or what do they mean?
In prediction accuracy, 50% is the ideal because ML modeling attacks uh, cannot learn and predict the next response only by guessing. And well, and that in prediction accuracy. In uniqueness, 50% is when two instances of the same architecture, you have a PUF1 and a PUF2, but both are the same architecture. If their responses or interhamming distance is more closely to 50%, that means that that both PUFs generate different responses. If it is higher, the PUF can generate patterns which the architecture can be easily modelable. And if the uniqueness is lower than 50%, well, both proofs are equal. And the uniformity must be 50%, because if it is higher than this value, the responses generated by the architecture will be logic ones. And if it is lower than 50%, generates more logic zeros.
Okay, that's interesting. Thank you so much for all of the knowledge you shared today. Thank you.
Thank you, Julio. We conclude this session. And we appreciate very much your assistance. Thanks very much.